Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover the dot product and its relation to length. So, a scalar product or dot product between two vectors, vector u, which is u1, comma u2 all the way up to un, and vector v, which is v1, v2 all the way up to vn, is defined to be u dot v, which is going to be the multiplication of their corresponding components. So we can see the u1, v1, which is the first corresponding component, plus the multiplication of the second corresponding component, so u2, v2, all the way up to un, vn. So what I want to do is I want to just compute the dot product between these two vectors, and then we'll talk about its relation to length. So, and distance, essentially. So, if I want to find the dot product between u and v, let's compute these by this way. So u dot v is going to be equal to, well, I have to multiply the first two components, so this is 3 times negative 2, plus the multiplication of the second component, so negative 1 times 0, plus the product of the third components, which is going to be 2 times 5. So then when we're done, we're going to have minus 6 plus 0 plus 10. So the dot product between these two vectors is going to be 4. Now the dot product can be, positive numbers, it can be negative numbers, it can be 0, and we'll see sometimes when the dot product is equal to 0, it does mean that there's something special about these two vectors that'll come up in the next lesson. So now let's look at the length of a vector, and we're going to go to 2 dimensions first because I want to show it to you geometrically, and then I can explain how this corresponds to the dot product. So if you want the length, say if I have a vector, say u, which is equal to, say, 3, 4. Now if I wanted to draw this vector, what I know is it's going to go 3 in the x and then 4 in the y. So that vector is going to look like this, our vector u. 3, 4. A little messy. Okay, so this is our vector u. If I want to find the length of this vector, well, what we know it comes down to is essentially a triangle that I'm going to need to know the base of the triangle, which I know is going to be equal to 3, and then the height of this triangle, which is going to be equal to 4. So then if I want to find, the length of u, L, is going to be equal to nothing more than the distance formula. So this is going to be equal to or I could say L squared is going to be equal to 3 squared plus 4 squared. So, this L being that length right here. So the Pythagorean theorem. So I could really say that L is nothing more than the square root of 3 squared plus 4 squared. So L is going to be equal to the square root of 9 plus 16, which is 25, which is going to be equal to 5. Now, this is nothing more than the distance formula, which is just the expansion of the Pythagorean theorem. So really what I can say is that if I want to find any magnitude of a vector, so I can say the magnitude of u is going to be the square root of the sum of the squares of all its components. So it's going to be a u1 squared plus a u2 squared plus a u3 squared, all the way up to, we now have un squared. So plus un squared. So if I want to compute the magnitude of say, this vector u, so example, if u is equal to 3, negative 1, 2, what is the magnitude of u? Compute the magnitude of u. Well, this is going to be the square root of the sum of the squares of its components, so this is going to be 3 squared plus negative 1 squared plus 2 squared. So we're going to have 9 plus 1 plus 4, which is going to be equal to the square root of 14. Now my claim in the beginning was that this has a relation to the dot product, and you can actually see, I don't know if you notice the dot product in here, but the magnitude of u is the square root of u dot u, which has got an interesting relation to, say, one-dimensional things or just your numbers that you looked at in algebra, that the square root of a number squared was the absolute value of that number, and this kind of has a very similar format to that, except remember these are multidimensional, so I can't really write this as u squared, I write this as u dot u. So the square root of u dot u is going to be the magnitude of u. Let's check that out. So this is going to be the square root. Well, u dot u, I'm just going to take the multiplication of the first components, but since I'm doing the same vector, it's just going to be 3 times 3, and then negative 1 times negative 1, and then finally plus 2 times 2. And then we can see that this is, the same thing as 9 plus 1 plus 4. So what we get here is the square root of 14.